Let's take another example here. In 2015, a total of 15.1% of US adults, where 16.7% are men and 13.6% are women, were smoking. So in this case then, the probability of event A, I assume it as A, is the total of the probability of having US adults smoking. Therefore, when I take a case of men as event B, the probability of B given of A, meaning the probability of men within these US adult smokers, will be equal to 16.7%. Now, if there is a question, what is the probability of a man and smoker in US? You can find it by calculating of probability of event A and B occurring together, because we are looking for probability of a man as well as a smoker. So probability of event A and B occurring together will be equal to probability of A, which is 0.151, multiplied by probability of B, given that event A occurs, which is 0.167. Okay, so this is an example of conditional probability. Another case example here, let's consider if HIV has a prevalence of 3% in San Francisco, and a particular HIV test has a false positive rate of 0.1% and a false negative rate of 1%, what is the probability that a random person selected off the street will test positive? So if we map this problem, there is a HIV positive of 3% in San Francisco, which means, okay, there should be 0.97 probability of negative HIV, right? And out of this positive HIV, the 3%, there are 0.1 false negative tests, right? Obviously, there will be 99% counterpart for a positive test in here. Okay, so there is 1%. Sorry, I guess I said 0.1%. There is 1% of false negative within this positive HIV, and obviously there will be 99% counterpart probability of having a positive test. In that case, then, the probability of having negative tests for a positive HIV patient will be equal to 0.03 times 0.01, which is 0.0003, as well as of a probability of having a positive test for positive patient will be equal to 0.03 times 0.99, which will be equal to 0.0297. I think this is pretty obvious, right? You have a 3% of positive HIV, and when they are having tests, 1% of it having a negative test, 99% of it they have positive tests. So the probability of having a negative test for a positive patient will be 0.0003, while the probability of having positive test for a positive patient will be 0.0297. Then we can do the same thing for a negative HIV patient. When we test a patient when we test someone, it's not patient here, when we test someone with a negative HIV, there might be a false positive, there might be a negative test result. And for a negative HIV patient, there will be a false positive of 0.1%, as it is mentioned in the problem here. So the probability of having a positive test for a negative HIV person will be equal to 0.97 times 0.001, which will be equal to 0.00097, as well as the probability of having negative tests for negatively HIV person will be equal to 0.97 times 0.999, which is equal to this number, 0.96903. Now, if we want to calculate the probability of probability of having a positive test, therefore it's just very simple. You just have to sum this number with this number, right? 0.0297 plus 0.00097, which is equal to 0.03067. So what this number means? This number means a probability of someone having positive test, regardless he is really negative or positive of HIV. Okay, so how to calculate the total probability? It is implied in the example, but the example that we just discussed. But mathematically, if we want to formulate it, total probability will be just simple summation of the joint probability in every event. So let's take a look on this mathematical expression. The total probability of event A, then it will be, what is this? This is the probability of event A and event B1 occurring together, plus probability of event A and event B2 occurring together, and so on and so forth, if there are n events of B. Okay, so to generalize the equation that we just discussed now, if there are more than 2 events, so what we have discussed till the previous slide is when we only have 2 events. How if we have multiple events, more than just 2 events? For more than 2 events, let's say we have n events of A, A1, A2 until An, the probability of all of the events occurring together, all of these events occurring together, so A1, A2, A3 until AN, all of them occurring together. So it will be, if you are referring to the Venn diagram, it will be the intersection of all of these Venn circles. Again, then the probability of all of these events occurring together will be just multiplication of, let's say, let's take an example of a 4 event case. We have A1, A2, A3, and A4. This is supposed to be 4. The probability of all of these 4 events occurring together will be equal to probability of A4, given that A1, A2, A3 occurring all together, times probability of A1, A2, A3 occurring together. This basically is derived from the first equation that we discussed previous slides before in conditional, 2 event conditional probability. So you can consider this as one event, right? So probability of event A given B times probability of event B. This will be equal to probability of event A occurring together with event B, right? So this first equation is simple. But then the last part here, we can expand it further. Probability of these 3 events occurring together, then it will be just simply as probability of event A3 given that A1 and A2 occurring together times probability of A1 and A2 occurring together. Okay, and this, the last term here, we can expand it again into this form. This is what we call as a chain rule. So probability of these 4 events occurring together will be equal to probability of A4 given A1, A2, A3 occurring together times probability of A3 given that A1 and A2 occurring together times probability of A2 given A1 times probability of A1.